Hello everybody, welcome back to part 5 of a 6-part series on combinatorics. Today we're going to be looking at this problem. Suppose that 40 indistinguishable people line up to buy a bottle of water. Each bottle of water costs 50 cents. However, 10 people in line only have a $1 note. The other 30 people carry a 50-cent piece. At the start, the cash register has no change. In how many ways can the people line up so that whenever someone with a dollar note tries to purchase a bottle of water, there's sufficient change for the transaction? Well, let's start thinking about sort of small ways in which we could order these people, and maybe this will lead to a good solution. So, if someone with a dollar note wants to buy water, or first of all, the first person in line cannot have a dollar note, because at the beginning there is no change, so there's no way for them to get for the transaction to go through properly. So the first person must be someone who has a 50-cent piece. Afterwards, then someone can go through with the transaction. So let's sort of model the cash register after certain transactions. So at first it's empty, and then the first person has to deposit a 50-cent piece. Now, the next person, it could be, let's say that the next person has a dollar note. So they pay $1, but they have to pay 50 cents. So they get the 50 cents back. So then we have $1 in the cash register. And now they have the bottle of water, and they only paid 50 cents because they paid $1 and they got 50 back. Now, the next person that goes up to pay, they cannot be someone that has a dollar note because there is only a dollar note in the cash register. So basically, we see that even if the cash register isn't totally empty, someone with a dollar note can only purchase water if there is a 50-cent note in there already. If there's not, then someone with a 50-cent note or a 50-cent piece has to go in and purchase something, because they won't take away any change. They will only deposit their 50 cents because they have the right amount for the transaction. So we sort of get a grasp about the situation, and since these people, the problem says that the people are indistinguishable, which means that we only care about the order of sort of $1 pieces and $5 pieces. So let's say people have $1, we will represent them with an O, and people with 50 cents will be an X. Then clearly we have an arrangement of 10 O's and 30 X's. And well, we're trying to find, let's say we're reading it this way. So this would be not a good ordering, because we can't have an O in the first slot. We have to have an X, and then we can have an O. But then we can't have another O. We can have an X. We can have two X's. So let's think about this situation. There's a 50 cent, and then a $1, and then a $1 and a 50 cent, and then a $1 and two 50 cents. Then basically the number of 50 cents in the cash register corresponds to the number of people with $1 notes that can purchase water for a given time. So then we could have two people with $1 notes buy water, but then we have to have more X's. So we sort of start thinking about, in the last video we had Catalan numbers, which were essentially grid walking problems, but we also corresponded the grid walking problems to a series of U's and R's corresponding to moves on the grid. And so we saw with the Catalan numbers we couldn't start with an up because we were bounded by the line y equals x. So we couldn't go up. We could only go right and then up. We could go right, right, and then up, up. So similar here, our rights are corresponding to people who have a 50-cent note or 50-cent piece, because we have to have these people paying before we can have $1 note people paying. And so now we sort of get the idea. So this is sort of a spin-off of the Catalan numbers. Instead, let's see if I can find sufficient grid space. I don't know if I can. Well, it is a very large grid, but let's just say, for example's sake, that this is our grid. I know it's not perfectly to scale, but this is the point 30, 10. And notice that after 10 people with 50-cent pieces pay, then the order after that doesn't matter. So instead of like a situation with the Catalan numbers where the line is sort of shifted, instead the line is still y equals x that we have to stay under, but it stops earlier. So we have this whole grid here that sort of doesn't matter, but we don't have to think about that. So we can still try and see if our approach with the Catalan numbers, which was to count the number of bad paths, we can see if that still holds. So if we have a bad path, let's say 2 people with 50-cent pieces pay, and then 3 people with $1 note pay. Obviously this is a bad path because that last $1 person can't pay. And so we see that similarly to the Catalan numbers, that we have to pass through this line y equals x plus 1. And so let's see if that reflection trick still works. Well, here we go. We're going from negative 1, 1 to this point. And then from here, we just continue on until we get to 30, 10. And so, like in the last video, I'm not going to show all the details of this bijection and how it works. I think that is more useful for anyone learning about bijections to sort of write down like actual reasons why this bijection must hold, which basically means that that any bad path corresponds to this reflected path or corresponds to its own reflected path, and that any reflected path corresponds to its own bad path. Likewise, we can count these bad paths after using our bijection by simply counting, well, this from negative 1 to 1 to 30, 10 is the same thing as 40, that was not a 4, 40, choose 9, those are the number of bad paths, and our total number of paths is just 40, choose 10. And I don't really feel like computing this, but basically this is the whole gist of solving this problem, is that you shouldn't take the Catalan numbers for granted. You should think about how they're defined and sort of the way or the main way that we define them, which is by creating this bijection, because it can be used to solve many other problems. It's not just the Catalan numbers, but this own, because Catalan is defined for a square grid, but we see here that it is also used for rectangular grids, which would be used in problems like these, where we have a system, and basically that system depends on a certain number of people going before another certain number of people. So yeah, that's basically the gist of this video. I just want to show that how bijections can be used to solve other types of problems that are similar to Catalan problems, but not exactly the same. This is why in mathematics it is always important to think about the method of solving a problem and not just the solution itself. Thank you for watching, and I'll see you in the last part.